Part 3, the last installment in today's video series, we are going to go through the GJK algorithm as you would implement it in actual programming code. So let's get to it. You'll recognize our two example shapes, the circle and the convex polygon. We'll be doing this example in 2 dimensions simply because it's easier to draw in 2 dimensions. The algorithm works in 2D and 3D. The 2D algorithm is a little simpler, but the same thing can be extended into 3 dimensions if you're making a 3-dimensional computational solver. GJK, as you'll remember, stands for Gilbert, Johnson, and Kearthy. That's the 3 authors of the famous GJK paper. What does it do? It allows us to relatively efficiently determine whether 2 convex shapes overlap. And we'll do that based on the Minkowski differences. We'll see whether the Minkowski difference of these 2 shapes encloses the origin. Now let me stress, we are not going to make the entire Minkowski difference. We've spent an entire video on what the Minkowski difference is. We're not going to create that at all. We're going to create individual points that are part of the Minkowski difference. And by choosing which points we create, we will efficiently determine whether or not those shapes overlap. Okay, we are going to introduce some more vocab words. We got a supporting point. A supporting point is a point on the surface of the shape that is the farthest in that direction. So, for example, I've got this convex shape here, convex polygonal shape. And so the farthest you can go in any given direction will be one of the vertices of that polyhedron. And so the supporting point on this shape in direction D is this point here that I've labeled P. So that is the farthest you can go in that direction. On a circle, you can do the same thing. The farthest you can go in that direction would be right there. Now, so for a circle or a sphere, there's an analytical solution to which is that point. And you just, do that with a little bit of a, you take this as a vector direction away from the center and go by the radius of the circle. That's where that point is. But for an arbitrary polyhedron, you would just go through the vertices and find the vertex that's the farthest in that direction. Let's talk briefly about how do you find the vertex that's farthest in that direction. Okay, think about that for a minute. We have a set of vertices. It's a finite set of points, and one of them is farther in that direction than all the others. How do we determine that? Let me suggest our old friend, the dot product. If you take the point from the origin to each of the individual points, which is simply the point, like point minus 0 is the point, take that vector, the position vector of the point, and dot it with D. The one with the largest positive value, or the largest value, not largest absolute value, but largest value numerically, is the one farthest in the direction D. People sometimes get confused about the idea that what I mean by positive or negative. Let's say the origin, for example, is there. What we're going to do is take vector P, which I'll draw as this arrow, and dot it with vector D. So vector D, I'll put it here. So what we get is the scalar projection there. So we got this length. And we will get a negative number because they point in opposite directions. So we'll get an answer for D that is negative. Consider a different point. Let's say this point here. Oh, that's better. Okay, that's pretty good. All right, let's take that P and let's dot that with our same D. And what we'll get, is this value. This much larger absolute value of D, or the dot product, but it is negative. So we'll have something like, for this point, we'll have something like minus 10, and for this point, we'll have like minus 2. And so minus 2 is greater than minus 10. That's the one we want. We will be going back and forth between Minkowski space and world space. And that can be rather confusing. As we get into a little bit, I'll do an example with diagrams, and that will help. What we'll be doing is talking about a supporting point, right? The supporting point is the point the farthest in any given direction. We will talk about supporting point in A, and we will talk about supporting point in B. We will also talk about a supporting point in the Minkowski difference. We'll say when we have the Minkowski difference, we'll be drawing that as a shape, point by point, and we'll say within that space we have supporting points. We don't have the full Minkowski difference. We just have these two shapes, and we'll be making individual points, supporting points within that Minkowski difference. We won't make the whole thing. Okay, let's stress that any given supporting point C is a point in A minus a point in B. For example, let's say we have a point in A, P0, that's right here, and a point in B, P1, that's right here. So we have a point in A, we have a point in B. If we subtract those two, P0 minus P1, that gives us a point we're calling C. The goal of GJK, as we explained in the very first video, was to take these points, P0 and P1, and try to pull them together. Now, mathematically, we're going to try to reduce P0 minus P1. Let me write that, in fact. Let's write that down. We're going to try and take C equals P0 minus P1. I'm going to try to drive that towards 0. How do we do that? Well, that means we're trying to drive P0 and P1 together. We're trying to drive those closer and closer together. And as we're driving P0 and P1 together, we're driving C towards 0. So the next search direction we want to search is the direction that takes C towards 0. That brings us to the next vocab word of the day. We have Minkowski difference. We have supporting point. We now have another vocab word, simplex. What is a simplex? A simplex is a set of points. It will be a set of points in the Minkowski difference. So we're building up parts of the Minkowski difference one point at a time, and we'll have a collection of points at any given moment, and we'll call that collection of points a simplex. A zero simplex is a single point. So when we started off with our initial guess, we take an initial guess and we subtract those 2 points. That's a zero simplex because presumably programmers learn to count from 0. So we have 1 point, so that's the zero simplex. When we add a second point, we go and we search and we say, okay, we've got this 1 point, we've got the zero simplex. Let's get a supporting direction. Let's find a new point. Now we're in Minkowski difference with 2 points. We have the original guess and this new point. We now have 2 points. 2 points makes a line segment. A line segment we will call a one simplex. And then what are we going to do? Well, it's iterative. So we have these 2 points. We're going to go back and find a new search direction. Go searching again. Go get a third point. Now that we have 3 points, 3 points makes a triangle. 3 points makes a triangle, and we'll call that triangle a two simplex. If we're in 2 dimensions, right, we're in a 2-dimensional space, that's the most complex shape we're going to need in 2 dimensions. But if we're in 3D, we'll have to go on to make a tetrahedron. If you've ever seen like a four-sided die or a triangular-based pyramid, that's a tetrahedron, which is the simplest 3-dimensional shape that we can make. So if you're in a 2D solution, you're done here. If you're going for a 3D solution, you will need to go all the way there. Now, why do you need to go, or why can you stop? Remember, if the shapes overlap, that means the origin is part of the Minkowski difference. What we're trying to do is build a shape that encloses the origin so that we can answer the question, is the origin part of this Minkowski difference? For example, let's say the origin is right there. That's inside this triangle. So that means that the Minkowski difference encloses or includes the origin, and that means those shapes do overlap. On the other hand, if the origin is over here, then so far the Minkowski difference does not enclose that point, and we can say so far we have not determined that the shapes overlap. We're not certain yet. There may be more points in the Minkowski difference that we need to explore. However, if we come over here to the 1 simplex, let's say I put the origin right here. Does that enclose the origin? No, a 1 simplex can't enclose anything. It's not complete yet. It's possible that the origin lies directly on the line between the 2 points, but in practice we don't bother solving for that. We consider that so rare that it's not worth adding the extra complexity to the algorithm. We'll go ahead and take it onto the triangle, and then we'll ask, is that point part of the triangle or not? Only when we get to that point do we bother adding that level of complexity. Okay, so how about the 3-dimensional solution? Well, let me draw this again. What if the origin is right there? Is that inside this volume or not? Well, we don't have a volume yet. We just have an area. This is a flat 2-dimensional thing. So like maybe this point is up out of the page a little bit. So we will need a 3-dimensional volume to enclose our origin. That brings us to the next vocab word, refining the simplex. We learned about a simplex. We saw that we have a 0, 1, 2, possibly a 3 simplex. And at each iterative step, what we do is we take the simplex we have and refine it. What does that mean? It means we take a look at the shape that we've got, and first we ask, does it enclose the origin? If it does not, we need to refine it. Refining it means, are there any of these points in our simplex that we no longer need, that are not helpful? If so, we'll throw those out and go looking for more points. We will always then go looking for more points. What direction should we look is really the question. We're always trying to, in Minkowski space, we're trying to enclose the origin. So when we go looking for more points, look in the direction towards the origin. We're trying to enclose the origin. So don't just look to go to the origin, try to go past the origin so that you can surround the origin. Right here it says the easiest simplex we need to deal with is a line segment, or a 1 simplex. Why don't we need to deal with the 0 simplex? Well, it's going to turn out when we see the full algorithm that we start with the 0 simplex when we make our initial guess. That'll give us the 0 simplex, and then the first thing we do is simply go straight towards the origin from there. So that's, I guess that's dealing with it, but we never have to throw out when we're down to a single point, we don't throw it out. We keep it and we search from there towards the origin. So that's very simple. No explanation needed. When we get that second point, now we have a line segment. We have a 1 simplex. Let's talk about what the options are. There are essentially, once we have a line segment, there are essentially 3 possible cases of where the origin is. The origin could be somewhere in the region past the end of the line segment. It could be somewhere between the ends of the line segment, or it could be somewhere in front of the beginning of the line segment. Right? This diagram should be bringing to mind stuff we talked about a few lectures ago when we talked about math problems you need to know how to solve. I'm asking, what is the closest point on this line segment to the origin? I have another point, the origin, and I want to know where on this line segment is closest to the origin. Is it point A is closest to the origin, point B is closest to the origin, or some point between A and B is closest to the origin. Like for example, let's say the origin is right here at Y. This is the origin. Then the closest point is right there where I have the little laser dot. We just need to answer the question, is it in front of A, is it behind B, or is it somewhere between A and B? Once we've answered that, we can look at that as three possibilities. If it's here at X, then it is beyond B. That's the first case I've got listed here. If that's the case, then I know that A is really not helping us with the situation. So I'm just going to remove A from my data set. I don't need A anymore. I will remove it from the simplex, throw it away, and I will search in a new search direction straight towards the origin from B. So I will simply go straight up that way. That's my new search direction. Go get me a new point. The next up, I have Y here is next, is that the closest point was here. If that's the closest point, then I'm going to keep both points. I am going to now try to build a triangle that encloses that somehow. And so that means I need a third point somewhere out here past Y. So I'm going to use as my search direction this perpendicular line that points straight in the direction towards the origin. I'm going to go search and try to get a point out here as far as I can so that will hopefully create a triangle that encloses the origin. The last point I have here is Z, and I note it cannot be Z. Why not? Well, remember, A was my initial guess. B is what I got by searching towards the origin from A. So B is definitely closer to the origin than A is. If it's not, then something has gone horribly wrong. So I don't actually even need to program this case, other than maybe you throw in an assert that says something has gone horribly wrong because this algorithm didn't work. So really the only two possibilities are that it could be out here at X or it could be somewhere at Y. And either way, I'm going to get a new search direction. And if it's at X, I will throw out A. If it's at Y, I'll keep both A and B. So what that means is at each step, you either throw out a point or you keep the points. If you keep the points, then you're marching your way along towards more and more complex simplex as you're doing your iterations. So if you were at the line segment and you kept both and you go and get a third point, you're going to take yourself from the one simplex to the two by adding that third point. On the other hand, if you had found that only point B was good, you would then drop back down to 0 simplex, then go do a search, and then it'll take you back again to the 1 simplex. The idea is that as you move along through the iterations, you're always adding a point. But sometimes you throw out an older point, and then go and get a newer point. So either you stay right where you are, or you march forward towards the more complicated shape. So we've talked about GJK in some detail now. We've learned what a Minkowski difference is. We learned what a simplex is. We learned about a supporting point and refining our simplex. Let's put it all together into an algorithm. Here it is. Start with an initial guess. We'll just say P0 in A and P1 in B. Some point that's guaranteed to be on the surface of each shape. Next, subtract those 2 points. P0 minus P1 gives us a point in Minkowski space C. This is your starting simplex. Just have a 0 simplex now. We will need a new search direction now to search for the additional point. We simply want to take C towards the origin. So towards the origin just means minus C. That will be our new search direction. We will now try to find a new supporting point. We'll call that point C prime in the direction of D. So P2 and P3 will be 2 new points. In shape A, we'll look for a new point P2 in the direction D. And in shape B, we'll search for point P3 which is in the direction minus D. Remember, we're trying to pull them together. So in one we search positive, in the other we search negative, trying to pull them across each other. So I'm calling the point in A here P2 and the point in B P3. Next up, we ask, this new point in the Minkowski difference, C prime, if it's already in the simplex that we have. At this point, we only have C. We have C as the only point in there. So if C prime is equal to C, then you give up, you're done. That's it, no intersection. That's the best we could do already. If C prime is not already somewhere in your simplex, then you add the point C prime to the simplex. So you've increased the complexity of your simplex. You have one extra point now. We now have C and C prime in the simplex. We will next ask, does the simplex enclose the origin? If the simplex encloses the origin, we're done. They do overlap. If they do not enclose the origin, then we refine the simplex, which is we ask, do we need to keep both of these points? Do we throw out one of the points? Give me a new search direction towards the origin, and we'll call that D prime, a new search direction, and we'll loop back up to part 4 to find a new supporting point. So that is the complete GJK algorithm. It's really not all that complicated. It just so happens that when you go and you research this online, you find a lot of very hard to follow explanations with all of this math basis and these complicated new vocab words. But I think if you simply look at it, it's only these 9 steps, then we've done worse things than that. So we can totally handle it. And if after all of that you find you're still somewhat confused, I found this explanation here to be really easy to understand. He goes through a lot of the same stuff that I've gone through, but perhaps seeing it spelled out in a different way can help you really complete that picture. And so finally, let's wrap this up with a demo. One more demo that I'll do here in PowerPoint. If we're doing this class live, as we do in some semesters, I will invite the class to come and participate and choose which points to do, and maybe draw this, project this up on the whiteboard and actually get out the dry erase markers and draw this up on the whiteboard. But as pre-recorded, I will do this myself. Let's take these two shapes, A and B, which you can see they do overlap. They do overlap right here. So we're looking for doing the GJK algorithm on these two shapes, and we expect that will enclose the origin. Let's take those two shapes and see how the algorithm works and how efficient actually it really is. All of these iterative steps with these 9 steps, and we're going to iterate over and over, can seem quite complicated, but it turns out it's not nearly as bad as it all sounds. So let's hit it. Let's start with our initial guess. For our initial guess, let's just take the obvious, which is A0, B0. A0 in shape A, B0 in shape B. And we will subtract them. So that is A0 minus B0. So let's take the vector A0 minus B0. So that's that red vector right there. So that's our first step. That vector represents a point in Minkowski space. So I've divided my slide here into world space on the left and Minkowski space on the right. Let's take this vector, which is a point now in Minkowski space, and plot that as a point in Minkowski space. I'll put a little dot on that point. There you go. So that dot represents a point in Minkowski space. I'll get the arrow out of the way. We now have a 0 simplex, and what we want to do is refine that. We'll take our search direction and we'll say, okay, what is the search direction? We want to head towards the origin from that. So how do we make that? Well, let's use my red thingy again. We want to search in that direction. So we want to take a point in A and move in that direction. So that's going to take us to pretty obviously, I think, and so that's going to take us to point A1. What about in B? In B, we want to search in the opposite direction. So I think it looks like it's pretty close, really, but I think B2 is more in that direction, more in the down left direction than B0 is. So I'm going to say my new shapes are A1 minus B2. So A1 minus B2 is this vector right there. Let's take that point over into Minkowski space. There you go. And I'll put a dot. I got a dot over here ready to go. Let's put that dot right there. All right. So now we have, let's connect those dots. Let's do like a connection, pow, and boing. It's not the straightest, is it? I don't know. That's not that important. That'd be that straight. Okay, so now I have this line segment, which is the one simplex. Next up, we refine it. Let's refine the one simplex. We ask that question, is the origin somewhere off beyond here? Is it beyond point 2 here, the second point in our space? And no, we can visually see that it's not. Remember, if you're programming this, you have to write the code to ask that question. And that's going to be, do some dot products, of course, and find out that no, the closest point on this line segment is right about here. Let's draw that. I'll use this line. It goes through the origin. Let's see if I can put it right on the origin there. And it should be perpendicular. I'm going to say that looks about perpendicular. I'm doing this by eyeball method, right? This is by eyeball method. And of course, you would have to program that. You'd have to write the mathematical expression for how to come up with that direction. So that gives us the search direction we want. We are going to keep both points, and the search direction now, which I'll draw in red, is, let's say, I'm trying to make it look exactly like my direction. There. So that's my search direction. So A, and shape A, I want to know the point farthest in that direction. I'm going to dot this vector with each of the points. Right, dot this vector with each of the points and say which one is farthest in that direction. Here's A0 and then A2. A2 is definitely farther in this direction than A0 is, but A1, I think, is even a little farther, so I've got A1 again. A1, again, is my best choice, but how about on shape B? On B, I want to aim in the opposite direction. That's clearly B0. So I want the vector, to make a vector, A1 minus B0, that is this vector. Let's take that over into Minkowski space, and I'll drop a point on that right there. And we can get rid of this line. In fact, I'm going to reuse this line to connect my two simplex now and make a two simplex. I will now ask, does this two simplex enclose the origin? And we'll see, yes, it does. We've gone through that in the previous lecture as well. Does this point, is the point 0, 0 lie within the triangle, or is it outside the triangle? In this case, we find it lies inside the triangle. And so with just 3 steps through the Minkowski loop, we found the two shapes do overlap. As one more example, let me do this again with 2 triangles that do not overlap. Let's do this whole thing again with the 2 triangles that don't overlap and see how that works out. Let's start with A0 minus B0 as our first step. Let's take that over to Minkowski space. Give me a point. Put that there. And get that line off of it. Okay. So we now have that first space. We're going to search towards the origin from there. So that means I'm not going to reverse the arrow. I'm just going to imagine that I have. So on shape A, I want to search in the direction of the tail of the arrow, and that's clearly that point there, A1. On shape B, I want to go towards the head, and that is B0. So I want to go towards A1 from B0. Let's make sure that's on that point. So that point is what we're going to take into Minkowski space there. Give me another point. Oh, come on. There we go. Give me a point right there, and let me connect it. All right, we asked the question now, does that shape enclose the origin? Well, it's still a line segment, so I can't close anything yet. Is our new point past, is the origin somewhere past there? No, not yet. It's still somewhere here. So our search direction, let's put the search direction in. We're going to do that perpendicular again. We want to search in that direction. So back here to the blue triangle, I think A2 is our best bet, and B0 on the green triangle. So this is our new point in the Minkowski difference. Let's put that on here and connect. I got another line segment up here. And then we ask, now does this shape enclose the origin? We run our algorithm of choice to ask, does that triangle enclose the origin? We say, no, it does not. What do we do next? We throw out one of the points. We don't need this point anymore. That point isn't helping us enclose the origin, so we refine the simplex. And we'll say, what is our new search direction? We want to search perpendicular to that line. I'm going to say that's this. So what is the point on the blue triangle most in that direction? I'm going to say that's really close, but I think A1. I think A1 is the closer one, and clearly it's B0 on that one. So boom, boom. Let's go and put that into Minkowski space and see what we got. And what we find is the point that we get is already in our simplex. We just repeated one of the points that's already in there, and that means we're done. We have just shown that that's the best. This line segment is the best we can do. That's the closest you can get to enclosing the origin. And what that is this line segment, right? You can see this line segment approaching this point is the best you can do in terms of causing those shapes to overlap. You can't get any closer. And in fact, the closest point is where we do that perpendicular that we talked about. Right, we make that perpendicular here, and that's right there. Right there where my cross is, that's the closest point between those two shapes. And there's still a gap there. So we have just shown that the two shapes do not overlap. All right, that's the end of today. That is GJK in a nutshell. We won't have time to implement this, and I haven't shown the last steps, which are what do I do now? Now that they do overlap, we're going to need more information. We're going to need to know what is the point of overlap, what is the normal on that shape, what do we do, how do we separate, right? And then build a whole physics system on top of that. So that's what that's going beyond the scope of what we'll handle in this class. What I will do, what you should expect to see on homework assignments and on exams is demos like this one. Only what I've done here is I've just eyeballed everything and just said sort of it looks like A1 is the closest. You'll need to show the math for those steps, the dot products and so forth. I would expect you to do that, look for something like that on the final exam, absolutely. Since this is a recorded lecture, Let me just say I have an assignment on Gradescope this semester for this, but depending on what semester you're watching this in, that may be in a different spot or not being assigned this semester or something like that. So what I can say for sure is go look on Blackboard for the schedule for this semester and see what assignments there are relating to this lecture. Okay, we'll see you in the next class.